Down in writing. So this is what I call my action potential flow chart. So we have a neuron that's at rest, about -70 millivolts. Some kind of a sensory stimulus can occur. Some kind of something you see, something you hear. If I went by, and I would not do this because I wouldn't touch you, but if I went by and like grabbed your shoulder real hard, that's a sensory stimulus. That is going to trigger some action potentials. If I had my hand sanitizer in here, or maybe if you guys could smell the orange I was just eating, that is a sensory stimulus. That may trigger an action potential in you. So either some type of sensory stimulus is going to occur that gets this neuron's activity in order, or a chemical message from another neuron. What's going to happen now is depolarization is going to happen. So depolarization is just getting less negative, going towards zero, due to loss of sodium. There needs to be enough sodium for an action potential to actually be triggered. Threshold met or exceeded. Now you know what's going to happen. So the next big thing that's going to happen is the sodium channels are going to open.
So those two happen at the same time then?
We want the sodium channels to open completely so we can get that huge influx. So now we know for sure an action potential is triggered. Does that make sense to you guys? Not all depolarization results in an action potential. Only if what? Only if the threshold is met or exceeded. Once the sodium channels open, because of the concentration gradient, what's going to happen? Sodium, what? Sodium rushes, I like that part, into the cell, or into the neuron. Right around that time, the potassium channels open. What's going to happen as a result of that? Because of the concentration gradient. Potassium is going to leave the cell or flow out of the cell. Sodium channels are open, the sodium rushes into the cell. We have potassium channels open, potassium rushes out of the cell. Let's go back to sodium. Closes. Sodium channels now closed. What's going to happen to the potassium channels eventually? They're also going to close. And once those are both closed, back to resting. Okay, neurons hanging out doing nothing, and then something happens to give it a little bit of a change. If the depolarization is strong enough, now the channels go, okay, hey, we're going to open. Sodium rushes in. Potassium channels also open. Potassium rushes out. Sodium closes, potassium closes, neurons back to rest. Just know that when the potassium channels open and the potassium leaves the cell, we start to now head back down. We call this repolarization. Right around this time, sodium channels close. Again, this is a process that's all kind of happening simultaneously. Okay, so they open, all the potassium gets to leave the cell, eventually they get to close. This little area here gets its own name. So here is resting potential. Do you see where we're kind of repolarizing so far down, like below the resting potential? Yeah. That's what we call hyperpolarization, below resting. Okay, so what we're looking at is the action potential spike. They could occur over 1,000 times a second. Like that is how fast, I mean, talk about splitting hairs. But the idea is the same. At rest, something happens, depolarization happens, sodium channels open, potassium channel open, they close, they close. Concentration gradient of lots of sodium somewhere. And now we're going to call this the absolute refractory period. Is when a second action potential by this neuron is not possible. The sodium channels are already open. Basically, there's no concentration gradient. Question for you. The sodium channels are open here. They're closed about here. Can another action potential possibly occur in this area? It could, but, what can you say about that next action potential? It would have to take a lot more depolarization. Because now it's starting from way down here, so now it really has to have a huge depolarization to get to meet or exceed the threshold. We call this the relative refractory period. That neuron could generate a second action potential. It's just unlikely. So it's not the action potential intensity itself, it's how many action potentials were generated from that sensory input. That's also a test question. So glad you asked, glad I mentioned the answer, you all better get that one right.
So sometimes you mention.
So too much potassium in the extracellular fluid will result in a ceasing or a stopping of all neural signaling. So how important are the pumps? Now, holy crap. Extremely. Oh, how about last week? One of the things that astrocytes do, look at your notes. I had you write it down. I said it'll make more sense to you. It's in the synapse. Is the synapse the intracellular fluid or extracellular fluid? That's extra. Astrocytes. So we have the sodium-potassium pump that is kind of governing how much potassium is in your extracellular fluid. And it pumps it out, gets it out of your extracellular fluid. And the astrocytes also are working hard to make sure you don't have too much potassium in your extracellular fluid. So we need, and there's probably other things out there doing the same job. Why do we have that redundancy? The all-in-one law. We know that either action potentials fire or they don't, and they all fire with the same intensity. That's the all-in-one law. How do we then differentiate a tap on the shoulder versus someone really scaring us? And so your two answers, and you may already have these in, I just want to be sure. Number one, number of neurons involved. Second thing, the rate of neural firing. That will also differentiate a weak stimulus from a strong stimulus.